We're going to take a look at some of the different groups on an aromatic ring and go through the mechanism of electrophilic aromatic substitution and analyze all of the different resonance structures and see what factors we can find that help stabilize or destabilize the carbocation intermediate. So the first thing we're going to look at is a weak activating group, which is an ortho-para director. We're going to look at the methyl group. So that's what we have right here on the ring, is a methyl group. And what we're going to do is look at ortho, para, and meta attack. And we know that methyl is an ortho para director, so the meta attack that we do is essentially a thought experiment. This doesn't happen, but these two do. So what we're going to try to do is figure out what makes these two pathways better than the pathway down here. So for ortho attack, what we want to do is end up putting the electrophile at one of the ortho positions. So I'm going to take this double bond on top, put my pencil down there, and draw a curved arrow to the electrophile. That gives me the electrophile right here and the carbocation here. Now, this carbocation is next to a pi bond, so we draw a resonance structure to get to this carbocation, and then because it's next to this pi bond, we can draw one more resonance structure going to here. So we get these three resonance structures under ortho attack. Now let's look at para attack. So para attack means we want the electrophile to add to the para position right here. So that means I need to use this pi bond on the bottom. So I'm going to put my pencil down there and draw the curved arrow to the electrophile. From here, we put the electrophile on the bottom carbon, and that gives us the carbocation right here. Similar to above, we can move the pi electrons and get a second and a third resonance structure. Finally, we want to take a look at meta attack. So meta attack means I want the electrophile right here at the meta position. I'm going to use the same pi electrons that I used in that para attack. The only difference is I'm putting the electrophile at this position, which leaves a positive charge down here. And again, we can move these pi electrons around to give two additional resonance structures. From here, it may not be readily apparent, but if you look closely, there's something special in the ortho and para intermediates. What we have that we don't have in the meta is this tertiary carbocation. Here, and in the para pathway, it shows up here. Compare that to the meta pathway. Every carbocation is just secondary. So the added stability that you get from this tertiary carbocation makes this pathway favored. And the fact that this carbocation ends up in both the ortho and para pathways is why this weak activating group like a methyl will give you both ortho and para products. So what we can say is that the extra stability that comes from the tertiary carbocation makes the ortho and para pathways preferred here.